Okay, so the first bit of news is, well, it's not news, hopefully, but the lab exam is this week in lab. And so getting ready for that is mostly just reviewing what you've done in the lab exercises. If you can't make it to your lab period, you can feel free to show up to the other lab to do the test. Anybody have any questions about the homework from Wednesday? Yeah. Okay. This is vectors. Where's that stuff? Okay. So number one, it starts out by giving you this vector that has a length of 50. And then it asks you to express the components in a couple of different coordinate systems, A, B, some rotated ones. Okay. So always with these kind of problems, what you're trying to do is find the angle from the positive x-axis of your coordinate system to the vector. Okay, that's always what you're trying to do for whatever the coordinate system is. And you never rotate the vector. I think that's probably the most common mistake people make is they're like, oh, this coordinate system's rotated. So they think like maybe the vector has to be rotated in some way to account for that. But the idea is that that vector just is what it is. You just move its tail to the origin of the coordinate system and then measure the angle. So let me draw the vector on these different things. So I'm gonna draw in there's the negative y-axis, there's the negative x-axis, and the vector is this. Okay, and it has a length of, it says this vector has a length of 50, so this has a length of 50. Okay, for this one, the negative x-axis is this, the negative y-axis is this, and the vector is this with a length of 50 again. Okay, for part C, you can see that the x-axis, I'll draw the negatives, but you can see that the x-axis is 30 degrees above a horizontal line. Well, that's where the vector is too. The vector is 30 degrees above a horizontal line. So that means that the vector in this case just goes right along that with a length of 50. Okay. And for this one, same thing, the vector is 30 degrees above that horizontal, so the vector just goes like this with a length of 50. Okay, I think that's probably more than half of the problem is just getting it positioned right on there. And then now one by one, it's just a matter of figuring out the counterclockwise angle from the x-axis to the vector. Or you can always go clockwise and call it a negative angle. So in this case, start at the positive x-axis and we want to go counterclockwise around to there. And so from the positive x-axis, it's 90 to get to the positive y, another 90 to get to the negative x, another 90 to get to the negative y, and then 30 more. Yes?
So would we always start at the positive x-axis whenever we're like trying to figure out the...
Exactly.
Okay, always.
Always, yep.
No matter
And
where it is.
and I think another thing that can be confusing for people is they have this sense that like, wait, are we talking about the real x-axis that goes like this? Or are we talking about the x-axis of the coordinate system, you know? But remember that this is only, we only think of this as the real coordinate system because we're the most used to it. Whatever coordinate system you're using, that's the x-axis that matters.
So then if you go down to B.
Yeah.
So then for B, it would be starting at down there.
Yep.
Right? And then
So that's the angle we want.
okay, and then for C, it would be starting from right there.
Right.
Always at.
Always. Yep. Exactly. Yep. So so this one, we said theta is equal to, I went 90 plus another 90 plus another 90 plus 30. So that is 300. And by the way, you can also always start at the positive x-axis and go clockwise if you call it a negative angle. So in this case, if you recognize that you could go clockwise from x to that red negative y-axis, and it would be 90. Well, we only want 60 of that because we're skipping 30 of it. So you could also call this negative 60. And, you know, in the math that you're used to doing, 300 and negative 60 are not equal to each other, but with trigonometric functions, it's the same thing. If you plug those both into sine and cosine, you get the exact same answers. So now we'll go 50 times the cosine of 300, 50 times the sine of 300, and let's see, that would be 43 point, nope, that would be 25, negative 43.3. Whether you use 300 or negative 60, you'd get the same thing. And so now for this second one, so this time, this angle theta is just going to be, we're going to go counterclockwise 90 plus another 30. And so that's 120 degrees. And so that vector is 50 times the cosine of 120, 50 times the sine of 120, and this time you get negative 25, positive 43.3. Okay, so now for these last two, this is something I want you to get used to just seeing is, so notice that that green arrow, we said that that's a trip with a distance of 50 along that arrow, okay? So this arrow for C is just lined up right in the positive x direction, okay? So when that happens, when that vector is along any one of those four positive or negative coordinate axes, you can just say the length of the vector in that direction, along that axis, and 0 for the other one. So in this case, that's 50 in the positive x and 0 for y. So you can just look at this and say 50, 0. You also could, I mean, the other approach still works. You could say that that's 50 times the cosine and sine of 0 degrees, and you'll get the same answer. But it's a lot easier to just visualize this. You can also visualize it. Remember that the components of a vector are the same as the coordinates of the head of the vector if the tail is at the origin. So what are the coordinates of that point? Well, it's right along the positive x-axis, so it's just going to be 50, 0. Same thing for this one, except it's along the positive y-axis. So this is just going to be 0 for x, 50 for y.
It made more sense to me explaining it now.
Okay, good. And if these were along the negative axes, they would just be negative 50, 0, or 0, negative 50. Any other homework questions you'd like to see? Okay. Well, last time, we talked about this stuff, introducing vectors. Now we're going to use this idea of vectors to talk about position, velocity, and acceleration in 2 dimensions. So now we need to define the position, velocity, acceleration, and displacement isn't something I'm going to emphasize a lot, but I'll mention what displacement means. All of these as vectors. So what does it mean when we talk about the position vector, velocity vector, acceleration vector? And when I talk about these, you'll know that I'm talking about a vector because I'll put an arrow over the top. So the position vector, the velocity vector, the acceleration vector, and then if we're talking about displacement, I'll use a lowercase d. So I'll start by defining the position vector. So if you think back to when I first defined position for one-dimensional motion, I said you had to choose 2 things before we could put a number on position. Anybody remember what those 2 things were? Yeah, so that's kind of one thing, I guess, the way I'm thinking of it. And then the other one, yes, exactly. You have to choose a 0 position to reference from, and you have to choose a positive direction. And now in 2 dimensions, there's kind of a new version of those things. So just as in 1D, you needed to, I was about to say define, but let's say choose a 0 position and a positive direction. In 2D, you need to choose an origin of the coordinate system and second, an orientation of the coordinate system. So like what we were just doing in that problem I just did, though the orientations of the coordinate system was given by the direction that x was pointing and the direction y was pointing. Not origin, orientation. Sorry. Orientation. orientation. And remember that both of these are in the real world. So you're basically saying, okay, I'm gonna put the origin here at this garbage can, and I'm gonna point the x-axis towards the door and the y-axis towards the clock. Okay, like real directions in the real world. We're not talking about some mathematical thing. Okay, and once you've done those, the position vector and I'll call it P with an arrow, is the vector from the origin to the object. Okay, so if you choose your origin to be here, your coordinate axes to be oriented like this, and at this instant the object is there, then the position vector is the vector that has its tail at the origin and its head at the object. That's the position vector. Maybe even a more intuitive way to think about this. And it means the exact same thing, is that the components of the position vector are just the coordinates of the object at any instant.
I have a question.
Yeah.
When we take like a quiz, one that we missed last time.
Yeah, let's do it next week. So I guess next Wednesday. I'll put that on D2L, but I didn't want to do it this week since we already had the lab test.
On D2L?
No, it'll be in class, just at the end of class.
Oh, okay.
Yeah. Okay, so for example, if this is our coordinate system, and I'll count off, let's say there's -1, -2, -3. And here's +1, 2, 3, 4. And let's say that the object is here. Okay, we're lined up with these that I put down. What are the coordinates of that object? 4, -3. And so that means that the position vector of that object at that instant is 4, -3. Just the coordinates of the object. The units of position vector, of the position vector, are always units of length. And that means that the SI units, the ones we're pretty much always going to use, are meters. Now, this is the one I said we're not going to use a ton, but the displacement vector is always just the position vector at the later instant minus the position vector at the earlier instant. Okay, so for example, let's say at one given instant, the object has a position vector that's equal to 5, -2. And at a later instant, the object has a position vector that's equal to -4, 0. What's the displacement vector? And to do that, you would just take the displacement vector is equal to -4, 0 minus 5, -2. And using the rules of vector addition and vector multiplication, you can think of this as multiplying that second one by -1 and then adding them. And anyways, what you get is -9 for the x component and +2 for the y component. Okay? And you can see that displacement also has to have the same units that position does. So in SI units, it would be meters. The next thing we have to define is the velocity vector. And just like it did in 1D, the velocity vector measures how quickly the position vector is changing. And one consequence of that is if an object is staying in the same location, the velocity is 0. Okay, so if the position vector isn't changing, in other words, the position vector is constant, then the velocity vector is 0, 0. The best way to think about the velocity vector is in terms of the two properties of a vector. Remember that all vectors have two properties. Anyone remember what these are?
Direction and magnitude.
Yeah, perfect. So magnitude and direction. And for the position vector, that didn't end up being a super useful way to think about it, even though a position vector also has those two magnitudes like every vector does. But for velocity, it's really useful to break it up into these two. So for the velocity vector, the magnitude is the object's speed at an instant. And the direction is the direction the object is moving at that instant.
I thought it was the length of an arrow.
Magnitude is the length of the arrow. Yep, that's what the magnitude is. Yep. So very often in problems, you're going to be given velocity information as a speed and as a direction. And I'll talk about how to combine those to come up with components for doing the problem. The units for velocity. Are always units of length divided by units of time. And so that means that the SI units are meters per second. I mean, if you look back at all the stuff we did with 1D, the units for position, velocity, and acceleration are the same in 1D and 2D. It's just that you represent them now as a vector instead. Okay, so here are 3 important facts to keep in mind about velocity vectors. So the first one, this is kind of what I just said. Often, maybe more often than not in problems, you'll need to calculate the components of V from a speed and a direction. So for example, that'll look something like this. A problem might say at the start of the motion, the object is moving 10 meters per second at an angle 30 degrees above the horizontal. Okay, so what that says is if this is the horizontal, like this is the ground, the object at the start of the motion has a velocity magnitude of 10 and makes an angle of 30 degrees with the horizontal or the ground like that. And then if you choose a coordinate system with the x-axis this way and the y-axis this way, then the components of the velocity vector, now it's just like the problems, the vector problems that you did over the weekend. The velocity vector components are just going to be 10 times the cosine of 30 degrees, 10 times the sine of 30 degrees, and that's 8.66 for x, 5 for y. Another way so the way we're going to use these components in equations is, in other words, Vx, that's the x component of the velocity vector, is 8.66 meters per second. And the y component of the velocity, Vy, is 5 meters per second. Okay? So that's all just that first of these 3 important facts. The second one, and I was just saying that next Wednesday we're going to have our first quiz, finally get around to the first quiz. These are the kind of questions that are very likely to pop up on the quizzes. You know, what are the three things I said to remember about velocity? Or so pay special attention to stuff like this. But the second one is what question? If an object is dropped, so if the problem says that an object is dropped, then at the instant it's dropped, at the instant it's released, its velocity vector is the same as what it's dropped from. Okay, so for example, if a car is going 30 meters per second, and you drop something out of the car window. So the car is going 30 meters per second this way. Well, if we can come up with the velocity vector of the car, and we can do that by choosing a coordinate system, the velocity vector is 30 meters per second this way. Since that's along the positive x-axis, the velocity vector of the car is 30, 0. So at the instant that the ball is released or the object is released, the velocity vector of the object is also 30, 0. Depending on the object and the velocity and stuff like that, that velocity could change really quickly. Like you can imagine if you're driving down the freeway and you hold a balloon out the window and let go of it, a second later the balloon is going to be on the road barely moving at all, you know. But at the instant you release it, it'll be going with the same velocity as the car. Okay? And just like in 1D, you know, I said, okay, so if something's dropped off a bridge, well, a bridge has no velocity. So at the instant you release it, the object also has no velocity. And again, in the other notation, we can say that the velocity of the object, x component is positive 30 meters per second. And the velocity of the object, y component, is 0. Okay, and then the last one is, so remember in 1D projectile motion, what did we know about an object when it reached the highest point in its flight?
0.
Velocity is 0, right. And so there's something you have to be a little careful about here. So the third one is when an object in 2D projectile motion reaches its highest point, only the y component of the velocity has to be equal to 0, okay? Not the x component. So like you might think, based on what we knew about 1D projectile motion, if I said, okay, guess what happens to the velocity when something reaches the highest point, probably most people would guess like, oh, I'll bet the velocity vector is 0. It's a reasonable guess. But it turns out that it's only the y component of the velocity, only the vertical component of the velocity, okay? And it makes sense if you think about it this way. So imagine, this pro baseball player throws this ball. Okay. And they can throw really fast. So this ball follows a path like this, okay? And let's say that the ball reaches its highest point here, okay? And let's say that you knew somehow that the ball's highest point was going to be there, and you weren't listening to this part of my lecture. You're texting or something, and so you assume that the velocity is going to be 0 there. And so you think like, I'm going to put a ladder up, and I'm going to have my head exactly where that ball is when it reaches its highest point. So here's you.
We've also
17 years of practice.
I guess that makes sense.
Yeah. Okay. So the question is, like, does that, just in your gut, does that feel like a good idea? You know, so if the velocity was 0 when that ball hit your head, it would be fine. That thing would just gently slow down, nuzzle gently up against the back of your head right as it reached that point, and you'd have no problem. You just like pick it up or whatever. But what really happens is this person throws that ball with some horizontal component of velocity and some vertical component of velocity. The horizontal component is, say, 80 miles an hour, okay? The vertical is 10 miles an hour, something like that, you know? And the vertical component will go from 10 miles per hour down to 0 at that point. So that does help a little. But the horizontal component, in this case, is going to stay at 80. And so that ball is still going to hit your head at 80 miles an hour. Okay. So just remember, I mean, this is just sort of a way to remember the x component is not going to be 0. The y component is the one that's going to be 0. Okay. So that's about all we need to say about the velocity vector. And now the acceleration vector. So remember when I introduced the velocity vector, I said that kind of the definition of the velocity is how quickly the position vector is changing. The acceleration vector is how quickly the velocity vector is changing. So the acceleration vector measures how quickly the velocity vector is changing. And so what that means is if the velocity vector is constant, the acceleration has to be 0. So in a problem or whatever, if I want to give you the information that the object's velocity is constant, I can tell it to you two ways. I can say the velocity is constant, or I can say the acceleration is 0. They mean the exact same thing. Okay. Now, here's something sort of new. In a way, this is kind of the only new thing that comes up in 2D as from 1D. In 1D, acceleration means that the object's speed is changing. But in 2D, it can mean two different things. So in 2D, acceleration can mean two things. The first one is it can still mean that the speed is changing. But it can also mean that the object is turning. Okay, so in one dimension, there's no such thing as turning. Everything is just moving back and forth along a line. Okay, in 2D, things can change the direction they're moving gradually without just repeating where they came from, going back over where they came from. And if you think about the fact that a velocity vector has a magnitude and a position, you can think, a magnitude and a direction, I mean. Speed change means that the magnitude of the velocity is changing, and turning means that the direction of the velocity is changing. So those are both ways that the velocity can change. Okay. The units of acceleration are length. Let me do it in the same format as before. So the units of acceleration are length over time squared, and the SI units are meters per second squared, just like in 1D.
Is that ever going to change?
No.
Okay. Not in this class, or just ever?
Never, ever, I guess.
Never?
Yeah, right. That's just what
Nice.
acceleration is, yeah. Although acceleration can get pretty mind-bendy when you get to like Einstein physics and stuff. But we're not doing that. Probably most of you won't be doing like modern physics kind of stuff like that. You know, you don't learn that in either the first 2 semesters of physics. Yeah. Okay. How did I write this before? I said 3 important facts about velocity. So let's do, well, let me just say this is one thing to keep in mind, one thing to notice about acceleration. When you're doing problems in free fall or projectile motion, so in free fall or projectile motion problems, the acceleration, the acceleration is always 9.81 meters per second squared directed down. That's not a surprise, you know, that's the same thing that happened in one-dimensional motion. And as far as components go, if you choose your y-axis pointing up, which is what I'm always going to do for free fall problems. So if you choose your y-axis to point up, then the acceleration vector is always going to be 0 for x, negative 9.81 for y. And by the way, this 9.81 meters per second squared is called lowercase g. Oh man, my computer's failing here. Bless you. Let's see. So you can also think of this as lowercase g pointing down. So sometimes you'll see that lowercase g, that's what it means. And that means as components, you could write the acceleration as 0, negative g. Okay.
For the negative 9.81.
Yeah, so remember that g is just, what g means is 9.81 meters per second squared. So you can, anytime you have 9.81 meters per second squared, you can replace it with g. Okay.
G stand for something?
Gravity, I assume, although I've never really heard that. Okay, anybody have any questions about those? That's it for defining those three things. So based on the order of steps that we did in learning about one-dimensional kinematics, anybody have a guess at what we're going to talk about now? We finished defining these things. What did we use those for? Yeah, then we got into problem solving. And so the next thing I introduced was the constant acceleration equations. Okay, and we're going to do the same thing here. It's just we're going to have more variables to consider because we have two components instead of one. So now we're going to talk about the constant acceleration equations in 2D. I'm going to first start by defining a couple things like I did before. The initial position vector and the initial velocity vector are the position and velocity at the instant when time is equal to 0. And PF and VF are the position and velocity at the instant time final. And then, like I was saying a few minutes ago, anytime you see an X subscript, so X subscripts mean X components of vectors. And Y subscripts mean Y components of vectors. Then the constant acceleration equations are, so I want you to notice that they're basically the same as they were in 1D. It's just now we have components and stuff. So I'm going to start by writing out the one-dimensional equations. So I'm going to start with, we had one that said V final is equal to V initial. Leave room for some subscripts here because we're going to put some X's and Y's in these. Plus A TF. And leave space for one equation below that. And then the second one said PF is equal to PI plus VI TF plus 1/2 A TF squared. And then the last one, leave space for another equation again, and the last one is 2A times the quantity PF minus PI is equal to VF squared minus VI squared. And now everything in these equations except the TF is a vector. So we have to put components on everything except T final. So in this one, I'm going to put X's on all these things. Everything but TF. And I'm going to do those for both of these two also. The TFs just stay the way they are. And now I'm going to do the same thing with all the X's replaced with Y's. So there's an equation here, VFY is equal to VIY plus AY times TF. There's an equation here that says PFY is equal to PIY plus VIYTF plus 1/2 AY TF squared. And then the last one is 2AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So it feels like a lot of stuff unless you break it down into the equations that you knew before and just recognize it's the different components. And notice that there are no equations that have X's and Y's in them. You only have X equations and Y equations, okay? So now I'm just going to give you a general set of steps for solving problems, and then we'll just get into some example problems. Probably not today. Maybe we'll do one. Okay, so how many total variables are there? With 1D, there were 6 variables. Now there's 11. There's still TF. And now everything else has 2 variables because an X and Y component. So now you have the acceleration vector, which is 2 variables. The initial position vector, that's another 2. P final vector, V initial vector, and V final vector. Okay, so here's the general steps. So the general steps for using the constant acceleration equations. Okay, so what was the first step in one-dimensional constant acceleration problems?
Try to find an equation where you.
That's a step, but not the first one. The first one was we had to choose 4 things: the 0 position, positive direction, time equals 0, and time final. And we're going to do the 2-dimensional versions of that to start. So we're going to choose, time still means the same thing, so we're still going to choose an instant for time equals 0. That's when you turn the stopwatch on. We'll choose an instant for time final. We'll choose an origin location. And again, this you can think of, it's in the real world, you can think of as a sticker that you place somewhere. And choose coordinate axis directions in the real world. Once you've done that, list out the variables you know and the variable you're trying to find. Third, and hopefully this is the last step, just like in 1D, try to find an equation that has the variable you want, with every other variable known. And in 1D, if you couldn't find an equation that works, what did you have to do? So this was the one that I had like in parentheses before, like sometimes you have to do this, hopefully not, but this was if no equation works, in 1D, I think what I said is you can solve for either time final or acceleration and then go back. In 2D, it's pretty much always going to be time final that you're going to try to find. So if no equation works, try to solve for time final and then go back to step 2. And in 2-dimensional motion, the reason that time final is so useful is notice when you look through these 6 equations, time final is the only one that crosses over between x and y component equations. So like a lot of times, for example, what we're going to do is use a y equation to solve for time final, and then we'll plug that into the corresponding x equation. Okay. All right, well, let's do one problem. What? If no equation works, solve for time final. And then go back to step 2. So I want you to notice as you're thinking through this stuff, don't think of this as all new stuff. think of it as just kind of extensions of the stuff you've already done with one dimension. Okay, so the example, let's say that a ball is thrown horizontally with a speed of 10 meters per second from a height of 4 meters. How far does the ball travel horizontally before it hits the ground? Okay, so let me just sketch out what's happening here. So this ball is thrown originally, it originally starts out moving horizontally from a height of 4 meters. And it's going to travel like a half parabola down to the ground. And we want to figure out this distance from here to here. Okay, so the first step is we have to choose the time equals 0, time final, and then a couple things about the coordinate system we're going to use. What do you want to choose as our time equals 0 instant? The choices here are made just the same as they were in one dimension. So time equals 0, when are we going to turn the stopwatch on? Yep, so that's the instant that it's thrown. And when are we going to turn the stopwatch off to look at the time?
Before it hits the ground. Sorry, the instant before that.
Yeah, right. And so, yeah, and we're going to call that, getting ahead of myself, but we're going to call that when it gets to position equals 0. But right, this is just the instant just before it hits the ground. And now we have to choose a coordinate system. I'm going to choose, this is pretty much what I'm always going to do in projectile motion problems. I'm going to put the origin on the ground underneath where the object is at the start. So I'm going to put the origin here, and I'm going to put my y-axis pointing up, and that makes my x-axis horizontal. So pretty much that's how I'm always going to do it. And now we have to think through what variables we know and what variable we're trying to find. Do we know how long it's going to take, what the stopwatch is going to say when the ball hits the ground? No. Do we know the acceleration? In projectile motion and free fall, we always know this. So if your y-axis is up, this acceleration vector is always just going to be 0, negative 9.81. Do we know the position of the ball at time 0? Yep, and remember we need components, and the components of that position vector are just the coordinates of the object. So it's going to be 0 for x and 4 for y. Do we know the position vector just before it hits the ground? Okay, so we know, right, I mean, that's, so what we know is we know that the y, if you think of these as coordinates, we know the y coordinate is going to be 0. So PFY is 0. But PFX is what we're trying to find. So here's a case where I'm breaking these two up. We know one, we're trying to find the other one. Okay, do we know the velocity at time 0? Well, we can figure it out because we know the speed and we know the direction. So I'm going to draw the coordinate system. We know that at time equals 0, the velocity vector looks like this with a magnitude of 10. So what are the components of that vector I just drew? You could think of it as 0 degrees and do 10 times cosine and sine of 0 degrees. Or you could say, you know, what are the coordinates at this point? This is a quicker, easier way to think about it. That's just along the positive x-axis, so it's going to be 10, 0. And then do we know anything about the velocity right before it hits the ground? No, so I'll just leave that off. Okay, so now the question is, do any of those 6 equations that I gave you solve for PFX given this stuff? Well, if we're trying to solve for something with an x component, we know it has to be one of these 3 x equations. So we've immediately eliminated 3 of them right off the bat. This first x equation here doesn't work because it doesn't have PFX in it. The second one has PFX, but it also has TF, so we don't know what that is. The fifth one has PFX, but it also has VFX, and we don't know what that is. So no equation works here.
Wait, how did you get the VI?
We were told that it starts out moving horizontally with a speed of 10. And so then I put the tail of that vector on the origin and found the components. Just like the vector homework that you did this week, or some of you, I guess, are probably doing it today still, but. Okay, so no equation works. And so instead, we want to see if we can solve for time final. Okay, and the one that's going to work, I mean, you could go through equation by equation and try to find this. 4 of those 6 equations have time final in them, so you could check all 4 of those. The one that we're going to be able to use here is PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. And we can at least check and make sure that works. We're trying to find TF, and it has that. PFY we know. PIY we know. VIY we know. AY we know. So this one should work. So I'll plug all this stuff in. It says 0 is equal to 4 plus 0 times TF, which is 0, plus 1/2 times negative 9.81 times TF squared. And if I move that second term over to the left side, we have negative 4.905 TF squared is equal to 4. Nope. When I move it over, this is positive. So positive 4.905 TF squared is equal to 4. Divide both sides by 4.905. And you get that TF squared is equal to 0.82. Now take the square root of both sides, and you get the TF is equal to plus or minus 0.9. Which one do we want? Positive 0.9 or negative? Yeah, this is time, so we never have negative time, so that makes it easy. So time final is 0.9 seconds. So it takes 0.9 seconds for this ball to travel until it hits the ground. And now that we know time final, now that's one more thing that we know here, and that gives us enough information to use this equation. PFX is equal to PIX plus plus VIX TF plus 1/2 AX TF squared. And we're going to use this to find PFX, the thing we wanted originally. So we have PFX is equal to, what's PIX? Zero, yep. What's VIX? 10. We just solved now for TF, so that's 0.9. This is the one that is easy to make a mistake on. What's AX? Because in one-dimensional motion, you only had one acceleration. Now we have two. Okay, so if you look up at that list, AX is 0. Okay, AY is the one that's negative 9.81. So this whole term goes away.
So AX is 0 and AY is the other one?
Yeah, right. And so now PFX is equal to 9.0 meters. Any questions about that? So I'll give you a problem or two sort of similar to this to work on for Wednesday. That's it.
Thank you.
Thank you.